Today we're going to have two presentations, one from students from the University of Sherbrooke and another from Université de Montréal. The first student is Étienne Lefrançois, who is a student in Louis Taillefer's group, and will present us what his work is about. So go ahead, Étienne.
Okay.
Just before you begin, do you prefer questions during your talk or after your talk?
During is fine, I think.
All right. So at any time, unmute yourself and ask a question if you have one. Thank you.
Okay, thank you. Okay, so thank you everybody for being here. Thank you for the RQMP for setting this up. Today I will present you some work I've done in during my master's degree, which I started in 2018, and it's about the thermal transport study in a Kitaev spin liquid candidate, alpha lithium chloride. First, the outline of the talk is pretty simple. I'll start by an introduction to the MOT insulator alpha lithium chloride. After, I will briefly mention the Kitaev model and its implications. Then I will just briefly mention the experimental technique, which is thermal conductivities, kappa XX and kappa XY. And then I will show some results we obtained from this study, and we will see that they can relate some results with phonons heat transport. And finally, if time permits, I will conclude. So first, let me briefly introduce you this material, which is an insulator, and this material has been studied a lot for the last years because it's a promising candidate for quantum spin liquids physics, and also all related with frustrated magnetism. So this material is it's an insulator which orders as antiferromagnetic long range. And so as we can see it in on the right upper panel here, you see that blue beads corresponds to ruthenium atoms, and they are surrounded by an octahedra made of chlorine atoms. And all the octahedra share with respect to the edges instead of the corner. So actually, ruthenium atoms form what we call a honeycomb lattice. And experimentally, this material is really fragile and soft, and it's really susceptible to suffer from stacking faults and defects really easily when it is handled in the lab. And also, this may be caused because the force between planes are stick via van der Waals force, and this material is really cleavable. And in the lower right, we see quickly we have some Venn diagram that maybe brings together some ingredients in order to have an effective spin 1/2 on every ruthenium sites. So large crystal field effects caused by the chlorine environment between the ruthenium, as well as strong spin-orbit coupling, splits band, and then generate some 1/2 spin effective. In the experimentally, here some magnetic phase diagram are shown in many studies, and they are all similar. But the ground state of this material is an antiferromagnet, which orders below 7 Kelvin, and this region lies up to around 7 Tesla also. So between 7 and 8 Tesla, depending on the studies. And after the you know, the HC that we call here, the critical field, we have what we call the polarized state, which is under debate right now. But one thing sure is that the long-range order is really well characterized and known over the studies. And some NMR, specific heat, magnetic susceptibility measurement are quite you know, coherent and similar within studies. So here, as an example, here I showed a specific heat as a function of temperature for different fields, and can track easily the nail temperature as we increase the field, for example. So about this material, what's really interesting for the past years, it's about one question that is under debate still from maybe 4 years, is whether or not a quantum spin liquid state lies between both ordered region. So meaning that, is there a narrow field range region in which we are susceptible to encounter some quantum spin liquids physics signatures? And before going further,
can I ask a question?
Sorry, yeah.
So what is this polarized phase? So here it's written QSL. So is it the quantum spin liquid, or?
Yeah, actually, maybe it's, I should have you know, take it off, but depending on studies, as I mentioned, it's not so clear what's about this state. Some studies claim that it's you know, an ordered spin polarized state, which you know, we recover an order, a spin order, while others say that it's more like a disordered phase. So depending on the studies. So,
okay. And other.
Sorry. Yeah.
The other question maybe is that usually the quantum spin liquids is related to singlet states. So it's kind of surprising to me that you have it at higher fields. Is it?
Yes, that's a good question actually. But, you know, if there is quantum spin liquid physics, it's really above that Tesla, 7 Tesla, sorry. So the question is under debate now, and that is the main question to ask, actually, okay, to address it.
Okay, thanks.
Okay, thanks. So without going further, I would just like to mention briefly what the Kitaev model, which is related to this material. And first, I would like just to highlight the Alexei Kitaev, which is a professor in Caltech, who in 2006 came up with this theoretical model, which gives a sense of a theory of a quantum spin liquid and a honeycomb lattice, which we can see here in the middle. So his model is based on a nearest neighbor exchange model here with nearest neighbor spins, and taking into account you know, a coupling K, a Kitaev interaction. And this model relies on the anisotropic bond interaction frustration. So just briefly mentioning that, for example, in the triangular lattice, we could imagine one spin up on a corner and its neighbor spin down, and while the other spin will fluctuate between top and up and down, sorry, configurations, because it cannot order antiferromagnetically, where as opposed on the square lattice, for example. So we can, in a honeycomb lattice, actually the spins can order antiferromagnetically without problems, but the Kitaev model here takes into account some you know, magnetic frustration, which is not caused by the geometry of the lattice, but rather because of the anisotropy of the bonds here. So the red bonds is not the same as the green and the blue, for example. And briefly, without going into details, what he did is that he solved exactly this model by you know, representing the spins operator in some fermionic operator. And this gives, like he mentioned in his work, it gives in thermal Hall transport here, the signature of Majorana fermions that can be detected as we go in low in temperature. So this model predicts some Majorana fermions at low temperature, which would have a quantized thermal Hall value, which would be equivalent to half of a thermal conductance quantum. So this is theoretical work done in 2017. So what we have to remember here is that the Kitaev model would predict Majorana fermions directly in the transverse heat transport. And so experimentally, about 12 years later, a Japanese group observed for the first time this Majorana fermions signature in the thermal Hall effect here. And so here we see that they observe as like a plateau, which would correspond to the signature of these Majorana fermions under here a narrow range of field. And so far this result has not been reproduced by any groups in the world. So we're interested in this question, and yes, because it's the most direct for us, the most direct signatures of Majorana fermions, and it's accessible via heat transport. And so again, in the same study here, they show the field phase diagram. Sorry, and we can see here that we have the same antiferromagnetic order here, and then the under debate phase here, which would be the polarized state. Let's call it this way. But they claim that over a narrow field range here, they observe this quantized value of thermal Hall effect. So here we have the thermal Hall effect as a function of temperature, and they see it in the under maybe 5K, where and then they observe under 5K also as a function of magnetic field. They observe the same plateau here, and so this is a good question to address. And then they claim also that this quantized value would be possible to be observed only for a certain quality of samples, which arise a question of, is it an intrinsic or extrinsic signatures? So this signature of Majorana fermions would happen only for high quality samples, or it is just an intrinsic properties regardless of how the conductivity behaves. So so this is how the question that scientists will want to ask right now. So briefly, the experimental technique we study here is the thermal conductivity kappa XX here. Is that we apply a heat current here longitudinally, and we can measure a thermal gradient dTx here, and when we apply a magnetic field perpendicular to the heat current, we can measure here dty, which is about 1,000 times smaller than the longitudinal measure. So this measure relies on an extremely well stabilized experimental conditions. So it's really hard to measure. So let me show you our results that we obtained over the last 2 years. So here you see a kappa XX as a function of temperature curve, which is the longitudinal thermal conductivity. And we see that over this temperature range, it's a phonon-driven thermal conductivity. So it's an insulator. We attribute this signal to phonons, and we see that around at 7 Kelvin here, where we enter the antiferromagnetic phase, and then we observe a strong suppression of the signal here, and it is most likely due to some spin fluctuations that would scatter more phonons here. And then when we enter down in lowest temperature, we enter the antiferromagnetic phase, we recover some increase of the thermal conductivity, which can mean that maybe some magnetic fluctuations or spins are gapped, and like scatter less phonons, so phonon can transport heat better here. And so here I compared the same curve with several samples that we prepared here in the laboratory, and we observed a great variation from samples to samples. So this is related to the question we addressed previously. Is the amplitude of this kappa XX, which can be correlated to the quality, the sample quality, is really responsible to the observation of the Majorana fermions in the Japanese study. So now I will show the kappa XY, sorry, the thermal hole conductivity as a function of temperature at 15 Tesla. And here we set ourselves in the configuration I mentioned previously, which is the magnetic field which is perpendicular to the heat current. And again, we see here at 7 Tesla the signature of the antiferromagnetic order, and we observe more or less the same temperature dependence. So, and by comparing some samples, we see also that they all show the same signature at low temperature, but again, the variation is quite sizable between samples. And then, here I compare the conductivities divided by temperature in order to give importance to low temperatures here as a function of temperature. And there was not much studies about these the transport properties of alpha ruthenium chloride, but here we see that our curve here is pretty comparable to two of their studies, but one shows a big kappa XX, and this purple curve was collected by the Japanese group, the same Japanese group that observed the Majorana fermions. And here again, this is the kappa XY over temperature as a function of temperature at 15 Tesla, and we report this increase of the thermal conductivity in the ordered phase, which can be explained again by the sudden gapping out of the spins, which would allow phonons to conduct heat more. But we are the only group to having observed this. Okay, so now we can then see and claim that we are qualitatively in agreement with some published data, but quantitatively it's really different so far. Here I show our data in the same sample, and we see that we compare directly the temperature dependence of both conductivities on the field, and we see that they show the same more or less behavior as a function of temperature. So this could be linked and coherent with our our interpretation of the phonons that could be responsible for thermal hole effects, since the temperature dependence is the same, and since we observe the same behavior in the ordered state. So now let me just highlight some results we have with when we applied the field along the thermal current. So by doing this, we're able to probe the magnetic phase diagram here and to suppress the ordered state in order to access this spin polarized state. So here, for example, I show some of the curves here, one at 4.5, when the purple one here, when we see a sudden increase of the kappa XX in the ordered phase here. When we're at 7 Tesla here, which is more or less the HC, the critical field, we observe the lowest signal here. And when we go into the spin polarized state, we observe a wide increase of the signal here. So that is, this shows that the scattering of phonons is maximal around the critical field, and that it might be due to some spin fluctuations near this boundary. And this also, exclude or tell to us that there is no sign of intermediate region that could host quantum spin liquids in this in our samples. But here I don't show any kappa XY measurement in this configuration because our sample were suffering from magnetic torque, and they were braked by the magnetic field when they were tilted in the field. So we haven't been able to observe some kappa XY data around this point here. And our results are pretty in agreement with what a 2018 study report here, which is the low temperature down to under 600 milli-K, which report a higher suppression of the kappa XX here around the critical field here. So our results are current with this study here. And this shows that this points towards the absence of Majorana fermions and quantum spin liquids physics because we don't observe any region here and any signs of quantum spin liquid physics. And the phonon scenario would be highly difficult to reconcile with some Kitaev's physics in this material. So to conclude, during the study, we observed that the phonon could be heat carriers both in the longitudinal and transverse conductivities because of the temperature dependence that are similar in the two channels. But we don't see any intermediate region that could host some exotic excitations like quantum spin liquid predicts. And the great variation from sample to sample may be caused by defects and other stacking faults in the crystals. So it's hard to reconcile with the Japanese group also. So on this, I would like to thank you.
All right, thank you very much, Etienne. Does anybody have a question? You can feel free to ask a question directly without raising your hand or anything.
Michel Côté, ici, j'ai une question. Would like to
Yes.
ask a question. You showed graph with a magnetic field of 15 Tesla for the the conductivity XY. Do you have like did you take this conductivity under many different fields to see what's the dependence on magnetic field?
Yes. For example, these panels here, we see that as you mentioned, the field is at 15 Tesla, but we also tried different fields. For example, like 5 Tesla and 10 Tesla, and we observed a reduction of the amplitude of the signal. So, for example, here, mostly for kappa XY here, we observed that, for example, the curve at 10 Tesla would be lower here, and the curve at 5 Tesla would be even lower as a function of temperature.
Were you able to determine if it was like a linear dependence or?
It appears that it's more likely sublinear rather than linear.
Okay. Yeah. Thank you.
Thanks.
I have another question also. So I'm not sure exactly what is the signature for Majorana fermion. Can you retell us what it is and what would you have needed to see in order to observe them?
Yeah, good question. Thanks. Actually, the only experimental signature we have for Majorana fermions in the heat transport here is this study here, the Japan group. So, for example, here in this panel, they show kappa XY over temperature as a function of temperature, and they see at under 5K, they observe a quantized value, a plateau here, corresponding to one half of the thermal quantum conductance here. So this is the direct signature of Majorana fermions in the transport.
And in your data, was it like too small of a signal, or I mean,
we haven't been able to measure the thermal Hall effect in this region so far, where they observed the Majorana fermions, because our sample were suffering from torque, so they were affected by the magnetic field that we applied, and then some broke and some just bent. So it was really hard to measure in these conditions. We haven't been able, but if you compare this signal here to the amplitude of the signal with our data, this signal is way much higher. So we haven't been able to, so far, to measure some comparable signal in amplitude.
Okay, thanks.
All right, so if there are no more questions, thank you again, Étienne, and we will go to the next presentation.
Yes, so the next presentation is from Véronique Brousseau-Couture. So she's one of my colleagues, a PhD student in a group of Michel Côté, and she has won numerous awards, but she works in the electron-phonon coupling of topological materials, and this is what she is going to talk about today, I presume. So Vero, the floor is yours. If you have any questions, you can unmute your mic and just ask it, I believe. So.
Yeah, sure. No, no problem about that. Well, in fact, I'm not going to be talking about electron-phonon coupling in topological materials. Instead, I'm going to talk about some other work which I did with a group in Belgium in the last years. So, which is about building the connection between the Fröhlich model and first principles regarding the 0-point renormalization of the band gap. So let me first start just by recalling one of the great achievements of quantum electrodynamics, which was explaining the Lamb shift. So as a refresher, the Lamb shift is a small energy difference that was observed experimentally between the 2s and 2p energy levels in hydrogen. And this difference could not be explained by the Dirac equation. So what QED brought to light was that, well, there's no such thing as an empty vacuum, and that what is now famously known as vacuum fluctuations is responsible for modifying the energy levels. So the process I'll be addressing today, we can see it as a condensed matter analog of the Lamb shift. So photons will be replaced by phonons. And just like in QED, the vacuum is never empty. In condensed matter, the ions are never at rest. And the consequence of this is that the electronic structure is modified by electron-phonon interaction. This gives rise to many observable phenomena, just a few of them being that the band gap will acquire temperature dependence, we have band broadening and finite quasi-particle lifetimes, and there's also polarionic systems that can display replica bands in their band structures. So in this talk, we'll specifically address the concept of 0-point renormalization of the band gap, or ZPR. So this is defined as the difference between the real physical gap that one would measure at absolute zero that takes into account all quantum effects, and what we call the bare or static gap, which is the gap energy one would get should the ions behave in a classical way and be at complete rest at absolute zero. So with that, a natural question to ask is, well, how can we actually measure this band gap experimentally? So of course, experimentalists cannot simply ask politely the ions to stop moving as they lower the temperature to make measurements. So instead, what we have to do is to take into account to take advantage of the fact that we know that at sufficiently high temperature, the system is going to behave classically. And in this regime, the gap energy will vary linearly with temperature. So with this knowledge, we can then take the high temperature slope, extrapolate it to t equal to absolute zero to get an experimental value for the bare gap. And one last thing I would like to point out before moving on is that, well, this bare gap here, from a purely computational point of view in the density functional theory framework, is actually a fairly easy quantity to compute, while obtaining the real gap, including the ZPR effect, is a much more computationally demanding. So the interest of the community for electron-phonon interaction is not new. One of the early models addressing this question is the Fröhlich model, which was developed in the 1950s. So the idea of this model is that it focuses on one single electron in the conduction band and one long wavelength LO phonon mode. So the idea in this model is that in polar system, if some ionic displacements along an LO mode will create small dipoles in the material, which at the macroscopic level will generate a polarization, hence an electric field to which the electron can couple. And at sufficiently strong coupling, this describes the idea of a polaron, which is a phonon cloud that's dynamically coupled to the electron. So this Fröhlich model is a founding block of the modern polaron studies and has shown to be extremely important to the current understanding the community has of the physical mechanisms underlying electron-phonon interaction. So here is the program for the remaining of my talk. So first, I will briefly explain how we can compute the ZPR from first principle, and I will compare some numerical results to experimental data. Then I will show how we can construct a generalized Fröhlich model starting from the first principle equation. And lastly, I will try to bring to light what does the importance of non-adiabatic effects in the ZPR tell us about the physical mechanisms that are at play. Okay, so one way to compute the ZPR from first principles is to start from the static equilibrium configuration and then use many-body perturbation theory. Now, within this framework, the change of an eigenvalue at a given temperature will be given by the real part of the electron-phonon self-energy. And should we apply the on the mass shell approximation, the self-energy will be evaluated at the bare electronic eigenvalue, which is the epsilon naught here. Then we can use the lowest order expansion of the electron-phonon interaction Hamiltonian and to construct the self-energy, which will contain two terms. The first of which here I'm showing as a Feynman diagram is called the fan term and contains two first order vertices that are treated as second order in perturbation theory. And the second one is called the Bywater term that contains a single second order vertex that is treated at first order in perturbation theory. And the sum of those two contributions is known in the literature as the Allen-Heine-Cardona theory, or AHC. So in this approach, the non-adiabatic effects enter only in the fan self-energy, which is given by this equation. So let me now guide you through some of the key elements of this expression. So first, here we have a sum on all phonon wave vector and branches throughout the Brillouin. In the brackets, we have two terms that respectively describe phonon absorption and emission processes, which are weighted by the electronic occupation factors. And lastly, in the denominators, we have this energy difference between the coupled eigenstates that comes from perturbation theory. And most importantly, we have the presence of the phonon frequencies, which is what makes this expression non-adiabatic. So historically, the AHC theory was first applied within the adiabatic approximation. And in this approximation, the phonon frequencies in the denominator are neglected by arguing that they're typically much smaller than the difference in electronic energies here. So adiabatic calculations were first made on materials like silicon and germanium and yielded good results with experiments. Then as computational resources became more and more accessible, then the community started to apply this framework to a broader class of materials. And at some point, the adiabatic approximation here was pointed out to be quite problematic for infrared active materials, as it was shown on, you can see on this graph that the ZPR diverges as we increase the phonon sampling here, which is completely not physical. So, and I would like to point out here that in polar material, this divergence will not build up should we consider should we include properly the phonon frequencies, even though the ZPR is going to converge quite slowly with the phonon sampling. So another method we can use, completely different method, to compute the ZPR from first principles is to do what I would call a numerical experiment. So we can take our lattice, expand it in a supercell, distort it by a given phonon mode, freeze this configuration, and then use density functional theory to compute both the total energy and eigenvalues. And then we can sample many different phonon amplitudes and combine them combine it properly by according to by weighting them, according to the phonon wave function. So this is what this expression means here. And with by doing this procedure, we can then obtain temperature-dependent eigenvalues. What I would like you to note here is that since we freeze in the perturbation, this method is inherently adiabatic. It assumes that in any configuration, well, the electrons will go into the ground state of this particular configuration. However, and contrary to perturbation theory, it does not assume that the eigenvalues are going to vary quadratically with the phonon amplitude. As you can see on this figure, there's a difference between the two green curves. But it retains the harmonic approximation for the total energy, and that can be seen here by the two blue curves that coincide here. Okay. So in order to study the importance of these non-adiabatic effects on the ZPR, one thing we can do is to compare numerical results from both approaches to experimental data. So here you have on the vertical axis, you have the first principle ZPR, and horizontal axis is the experimental value. And I would like you to note here that both these axes have log scales. So the blue disk here represent non-adiabatic AHC calculations, while the red triangles stand for adiabatic supercell calculations. So the first thing I would like you to note from this figure is that if we look at the blue disks, all of them except two lie inside the shaded gray area, which was our 25% accuracy target compared to experimental data. By contrast, more than half of the red triangles lie outside this region. Hence, this clearly shows that the non-adiabatic methodology has better predictive capabilities compared to the adiabatic supercells. And moreover, if we look at the most ionic materials in the set, namely the oxide and sulfide, two of them being here in the figure, then the difference gets even more significant and can reach a factor of 2. And this suggests that the Fröhlich interaction I was talking about earlier, which is completely absent from the supercell at the adiabatic approach, might be the leading electron-phonon coupling mechanism in these materials. So, in order to verify this hypothesis, what I will do now is to construct a generalized Fröhlich model starting from the first principle equation. So the idea behind this is to retain some of the fundamental assumptions that were made by Fröhlich, namely that the ZPR will arise from dielectric interaction with a long wavelength of phonon, and that it is dominated by the zone center parameters, including the phonon frequencies. So this construction will give us a way to quantify the importance of the non-adiabatic effects in the full first principles ZPR. So what we will do is we will start from the fan self-energy and consider one electron in the conduction band. The first thing we will do is to consider only couplings in the subset of bands that is degenerate to the band extrema. So we cancel out everything else, and then we will take the long wavelength limit for this expression. Then we retain only contributions from the LO phonon modes, and we take the continuum limit. And lastly, what I would like you to look at now are these blue terms I've emphasized on the last equation. And what I want you to see is that should I apply the adiabatic approximation to this expression and eliminate this phonon frequency term here, well, we would be left with a 1/q² dependency, which is precisely here the mathematical source of the adiabatic divergence I was mentioning earlier. And this divergence can only be integrated should we keep explicitly the phonon frequency in the expression. Now, after a few more simplifications,
I'm sorry,
yes.
Can I ask a question?
Yeah, sure.
Can you go back to the previous slide?
Yes.
So what was the rationale for neglecting interband transitions again?
It's one of the fundamental, the interband, you mean?
Yeah, that you threw them.
It's one of the fundamental assumptions that was made by Fröhlich. So what we're trying to do is just to generalize the Fröhlich model to real materials, and the original Fröhlich model considers only interaction within the same band. So.
Okay, and is that accurate? That assumption, or?
If it's accurate, well. If it's accurate, of course, it's not going. We're not with this assumption. We're not going to be able to capture the full ZPR. So we don't expect this model to reproduce the first principle ZPR. We expect it to just be able to capture and focus only on the part of the ZPR which specifically generated by non-adiabatic effects. So that's the purpose here.
The other question that I had, or maybe it's related, the Debye-Waller contribution is also neglected. Is it because interband transitions are neglected also? Or?
Yeah, it's the same idea. So we're just starting with we're just reproducing the Fröhlich methodology. So neglecting the same types of contributions that was neglected by in the original Fröhlich model. So, but we just want the model to be able to describe real materials, like with degeneracies at the band extrema and so on. So we're not expecting this to be a model of the full ZPR. So we're completely aware that we're neglecting a lot of things.
Okay, thank you.
Okay, so that's the expression we're left with. That's going to be our generalized Fröhlich model. So what I want you to see in this is that, well, it only depends on a few key parameters that I'm showing here. So the phonon frequencies, we have the mode polarity, dielectric constant, and effective mass, as well as their respective angular dependency. And these parameters can be very quickly and easily evaluated from first principles. So as I was just explaining by answering the question, we retained from Fröhlich some of the original approximation and from this model. So we assume that we have a flat phonon dispersion, parabolic electronic bands, and we keep only the fan interband contribution. But by contrast to the original Fröhlich model, our model is able to account for multiple phonon branches, LO phonon branches, for degenerate and anisotropic band extrema, as well as band extrema that can be located anywhere in the Brillouin zone. So what I'm showing you now, so we have on the vertical axis, we have the ZPR that was computed with the generalized Fröhlich model and compared on the horizontal axis to the first non-adiabatic AHC ZPR. Okay, and again, both axes have log scales here. So first, what I want you to consider are the most ionic materials in the set. So we have the oxides here in the purple disc, and we have the chalcogenides, which are the yellow squares. So for these materials, the generalized Fröhlich model is able to account for more than 2/3 of the full first principle ZPR. So that means that the idea behind the Fröhlich model, so the large polarized picture, is what's going on in these types of material, and that the non-adiabatic effects here are clearly the leading type of contribution in these materials. If we consider now less ionic materials that still contain lighter atoms and that have high LO frequencies, like the nitrites here, which are the green diamonds, and silicon carbide, which is the light blue hexagon, we can see that the contribution of from the Fröhlich model is still significant. For these materials, about between 40 and 60%. But should we consider less ionic 3,5 materials with heavier atoms, which are the blue triangles in this region here, we can see that the Fröhlich model is less and less predictive in a certain way. And what that means is not that the Fröhlich model is not good. It means simply that in these materials, the Fröhlich interaction is not the leading contribution, and that other types of interactions, such as interband coupling, the Debye-Waller interaction, as well as coupling to acoustic modes, play a greater part in the ZPR for these materials. Okay, so with these results, that brings it to the question, well, why are the phonon frequencies so important in the polar materials? So to answer this question, we will consider a very simple, very simple model. So first recall that the self-energy GO has this 1/energy difference dependency, and that this energy difference, which I'll call delta E, goes roughly as Q square in the small q limit. So what we're going to do is we're going to combine two electronic states at k and k plus q. And from undergrad wave mechanics, we know that by doing so, the wave function is going to have this sort of beating pattern like this. So we will now also take LO phonon, consider the LO phonon potential, which will take the crystal potential and lower it periodically in space. So when we apply the adiabatic approximation, so what we are assuming is that the electron can always localize where it can lower its potential and energy. So hence the charge density will be sort of always align and the electron will want to instantaneously localize here along the minimum of the phonon potential. But should we consider the dynamics of this interaction properly, what we have to take into account that the phonon potential oscillate, hence the location of the minima is going to change in time. And then if we recall that our wave function was constructed with states that have an energy difference delta E, then we know from the energy time uncertainty principle that moving like this wave function across a characteristic distance is going to take some kind of characteristic time tau, which goes as roughly 1/delta E. And then so what's happening here is that in the long wavelength limit, so in the Fröhlich limit, what we know is that this delta E can get arbitrarily small. So what's happening here physically, what that tells us is that when this electronic characteristic time tau becomes greater than the phonon characteristic time that goes over as 1 over the frequency, well, the electron is simply too slow to be able to follow the fast-moving phonon potential. Hence, it cannot fully benefit from the lowering of the potential like it did in the adiabatic picture. So,
I'm sorry.
Yes.
Let me ask you a question. This electronic
Sure.
tau, again, can you tell me where it comes from? It's over delta?
It's energy time uncertainty principle. You have like delta E, well, or delta time that goes as h bar over 2 simply.
What was delta epsilon there? I'm sorry.
Delta epsilon here, it's the difference between the electronic states you're coupling. So in the long wavelength limit, what I mean is that this delta epsilon is going to get really small, so the characteristic time will get very large, and at some point it's going to be bigger than the phonon.
Yes.
The phonon characteristic time. So the electron simply cannot fully adjust instantaneously to the lowering the phonon potential like we would like what occurs in the adiabatic case.
And here, I guess you're neglecting any disorder effects, but if you have, say, finite disorder in your system, that could also participate in this electronic tau, you know, the scattering time of the electrons.
Yeah, absolutely. So what I wanted to do here was just to give an intuitive picture of what do these non-adiabatic effects are capturing physically. So of course it's very simple. It's the simplest model I could think of. So it's really a simplification. So that's not.
Yeah, I think what you're saying is interesting, that if tau is bigger than tau phonon, electrons has no time to adjust. And but I wonder if that tau there, in your case, that tau is very big, as you say, when Q goes to 0, right? But if you have some realistic system with disorder or something, that tau would be maybe limited by scattering time of electrons.
Yeah, probably it would be limited. But
and then you would have to compare the scattering time with the phonon frequency or something.
Yeah, probably that's an interesting. I didn't think about that. I haven't thought about that, but that's an interesting point of view. Fine.
Okay,
No, but let me add, if there is another tau due to scattering, it will impose a lower limit, not a maximum limit. And so what Véronique is saying, tau will get even, I mean, this tau it's not the imaginary part, okay, in the self-energy. That's not the same thing. It's just the frequency response of the linear combination of the wave functions. So there's two different things here. And so there is like in the denominator that Véronique wrote on this page, there is like probably an imaginary part to it.
Yeah, there is. I just removed it for simplicity.
But she's talking about the time integration, because this is what these integrals are done in frequencies usually within the perturbation theory. But if you put that back into time, what does it mean? It means that the linear combination of wave function is actually moving slowly in time.
But it's just a nomenclature, but I would call this time an electron hole characteristic time, not the electron.
Okay.
Okay, yeah.
So it makes more sense in the sense that the electron hole is more like charge and you're coupling to charge.
Yeah, okay.
Now we see the wise André-Marie talking.
Just nomenclature.
Okay, thank you.
Okay. Well, where was I with that? So the basic idea I want you to get from this slide is that, well, in the long wavelength limit, so as in the Q goes to 0 limit, the adiabatic approximation simply is not able to capture the real physical mechanism which is in play in the electron-phonon interaction, which is namely like this slow electron physics. And what I find interesting is that it's precisely like what Fröhlich and Feynman cautioned us in their original papers like 60 years ago. So so just in summary, what I've shown you was that the ZPR in polar materials is dominated by the slow and non-adiabatic response of electron to the fast-moving phonons, and that including these effects in ZPR calculations is essential for global agreement with experimental data. With that, I would like to thank all my collaborators that worked with me on this project. From a lot of different institutions. I would like to thank the sources of funding. And with that, I would like to thank you for your attention.
Thank you, Véronique. Are there any questions? So I have a question, maybe just to come back to this adiabatic approximation. So maybe go to your slide 8. So in the first principle approach,
8.
Okay, maybe here, yeah. 7, no,
7?
6.
This.
So yeah, so this is the first principle approach, right?
Yeah, that's the first principle. That's the perturbative approach.
Okay, so in the first principle approach, do you retain these phonons frequencies?
What we did, both of the approaches have been used in the literature, so that's why I wanted to emphasize. So the real equations, if you you do your perturbative approach properly using the Green's function, you're going to have the phonon frequencies. But historically, the HC theory, it was developed in around 1980, 85. And at the time, while computer resources were limited, and the way I see it is that, if you make the adiabatic approximation here, you can see that the electronic occupation terms cancel out and it gets easier to compute. And also the original application of the adiabatic approximation was for non-polar materials. So it was for silicon, for germanium. So, and in that case, we do not have this polar coupling. So there's no divergence and it works really well. But for probably historical reasons, it kept being used within the perturbative approach in the following years for different materials until it was like identified by this work of Samuel Poncet as like being yielding like a divergence.
But in your case,
in our case, in my case, we're using the full equation, so we're retaining the phonon frequencies.
So maybe just at slide 8, then I'm wondering. Your graph looks like quite better. Maybe just there's cadmium telluride that's getting worse. So any comments on that? And perhaps this leads me to asking what's missing within this first principle. What do you think is the next step, basically? Do you have any idea?
Okay. Well, one thing I didn't say during the talk for time reason is that in this graph, we also considered the change of the gap energy that's induced by the what we call the 0-point lattice effect. So the change of the lattice parameters that is induced by the presence of phonons. So that has been taken into account for both approaches. But for your question regarding cadmium telluride, so these calculations were all done without spin-orbit coupling. So in the end, since I've been working on trying to characterize what's the effect of adding spin-orbit coupling on the electron-phonon interaction, both for the full first principles approach and the Fröhlich model. And what I can tell you is that just considering spin-orbit coupling brings the cadmium telluride inside the 25% region. Yeah.
Okay. And any next step, maybe? Or is this the best we can do? Or?
Well, the best we can do, there's one thing I didn't emphasize about is that, well, we know that the non-adiabatic effects are crucial for predictive capabilities of the method. But one thing that is that we not consider right now in the non-adiabatic HC approach are like higher order terms. So we're at
first order.
The lowest order and perturbation theory. So we have the harmonic approximation. And if we look so at this graph, so basically we're only sampling like small displacements here in the region. If you look at the green curves where the eigenvalue is quadratic with the phonon amplitude. But should we include higher order terms, then at some point, you can see that the eigenvalue starts entering like a linear regime as a function of phonon amplitude. So typically, so this work by Gabriel Antonius shows it very nicely. So typically what it does is that it reduces slightly the electron-phonon coupling energy. So it could reduce slightly the ZPR. So that could, in a certain way, take some of the materials, just like
okay, thank you.
Reduce a few of them. So yeah, I think Eric has a question.
Yeah, Eric next.
Yeah. So thanks for the nice talk. It was interesting. So at the beginning, you present this work as you have the static value for the band gap, and then you will obtain corrections. But my question is do you have in the band theory, do you need a material that is an insulator, or could you just start from 0 band gap and then? So I'm thinking about, for example, mott insulators or something like that, which only become insulators because of interactions. So I wonder if you can describe these kind of material which don't have non-zero static value for the band gap?
Okay, so sorry, your question was quite long. I'm just figuring out. Can you just repeat?
So yeah,
just in like 3 words.
Materials that are not insulators in the band theory.
Okay.
So that don't have a static, a non-zero band gap.
Okay. Yeah. Well, I know that this kind of theory can be used. I know it can be used for metals, like just metals that are described by band theory. So I've never really worked in metals, but from what I know, typically the Debye-Waller term is neglected in that case. But I know it's been used on like LSCO or some of the cuprates semiconductors. I know that the electron-phonon interaction was studied in these materials, so I guess it's the machinery can be used. But as for your question about like Mott insulators, well, I think that one of the starting you need to have at least a good starting point, especially if you're using perturbation theory. You want to use like your equilibrium static system, and you want to take the phonon frequencies that come from this system, so in order to compute the ZPR. So I guess you would have maybe not start from just band theory and use like other methods, like maybe I think DFT plus U can account for Mott insulators, or other. I'm not exactly sure about that, but I guess you would have to start from like more advanced theories, just even for the static configuration, before applying these, in order to be sure that your equilibrium system, which is your starting point around which you do your perturbation theory, is in some way well described. So
okay, thank you.
Next we had André-Marie, maybe. Do you still have a question? Or?
Oh, it was the same question.
Okay. So are there any last question? So if not, let's thank Vero again for a nice talk, and we'll see next week, I guess. Yes, we have a talk next week.